This call is now being recorded.
Okay, we will start with something called crystal bonding. Now, till now, we discussed what is crystal structure and how to determine crystal structure. But then, obvious question that arises is how exactly the crystals are being made. Right? Crystals are made out of atoms, and then atoms or molecules, right? So, how can one atom is attached to another atom? So there must be some kind of force of attraction, and that force of attraction is termed as bonding, chemical bonding. Okay, so expected outcome from this chapter would be explain how atoms bond together to form crystal, then classify these crystals such as ionic, covalent, metallic, hydrogen bond, or van der Waals. Then correlate the characteristic properties of solids with nature of bonding. So what kind of bonding will show what kind of characteristics? And derive expression for cohesive energy for ionic and van der Waals system. So this will be our M. So how do atoms cling together? How do atoms cling together? Or what is the reason? The reason is what is the reason for this cohesive energy? So that two atoms are kind of attached to each other. So saying that solid matter exists in three states, right? Matter exists in three states: solid, liquid, and gas. In solids, the atoms are closely packed, and according to Bohr's theory, an atom consists of nucleus and the center of at the center, and the electrons revolve around it with fixed orbits. Since the nucleus carries almost entire mass of the atom, it is considered to be at rest, and this may lead to the consideration of orbital electrons are responsible for most of the characteristics of the solid. Orbital electrons. Okay. But you may be on the right track where the properties of matter also depend on the way orbital electrons arrange themselves. It is not only that they are in the orbitals, but the properties. This is important. The properties of the matter depend on the way the electrons arrange themselves around the nucleus, giving rise to bonding among themselves, bonding among atoms. The nature of bonding among atoms depends on the electronic configuration and the energy of the system. There are two factors responsible for that. One is electronic configuration. First one is electronic configuration, number one. Number two, the energy of the system. The energy of the system. The consideration of energy arises from the fact, the consideration of the energy arises from the fact that all bound systems should have minimum energy in their stable form. All bound states. Hmm. So, consideration of energy arises from the fact that that all bound systems should have in the minimum energy in their stable form. If we are talking about stable form, then the energy must be minimum. Energy must be minimum. Okay. If we look at the potential profile, we look at the potential profile. So what exactly it is telling? It is telling uh, distance versus energy. Distance versus energy. Okay. Distance versus energy. So this is energy and this is distance. Distance means interatomic. The variation of energy with of an atomic system with separation between the constituent atoms. Interatomic distance. Interatomic distance. So if you bring one force is attractive. One part is attractive. One part is attractive. Another part is repulsive. And depending on attractive and repulsive ratio, what happens? Let me see that figure if they have written that. No. So what will happen? The system will somewhat be somewhat like this kind of one. So the energy will be repulsive if they come very close to each other. If you bring two atoms very close to each other, they will be repulsive. But mm, beyond certain beyond certain distance, they will their energy will be negative. Their energy will be this part. Their energy is negative. Energy is negative means they are attractive. They're attractive in nature. So there is kind of a bonding. There is kind of a bonding. Okay. Is this part clear to everybody?
Yes, sir.
Now, when some of the it is explaining actually, when some atoms combine to form a stable molecule, it is implied that it is a minimum energy state. When two atoms which form a molecule are brought closer to each other, they first experience attractive force between them because as you move from this side, from larger distance to smaller distance, so they will feel attractive. Yeah, there will there will be attractive force between them. When the atoms becomes too close, repulsive force come into picture. When the atoms become too close, when the atoms are beyond in this part, then it is repulsive in nature. Because the energy is positive, so they will be repulsive. Energy is negative, then it is the potential energy is equal. Energy is negative, that means it is attractive in nature. Okay. To express the above description situation mathematically, let us assume that the energy due to attraction is UA, U attraction UA, and repulsive energy is UR. Eh, So if you are talking about UA, then it is proportional to 1 by R to the power M. 1 by R to the power M. Okay. And U attractive will be equal to some minus A times R to the power M. Minus A times R to the power M. This is attractive. Then if you think of repulsive, then it will again be proportional to 1 by R to the power n. It might not be same as R, M and N might not be same. So that's why the final equation would be minus A by R to the power n plus B by R to the power n. Okay, this is basically your energy. This is basically your energy. Okay, now note that the minimum, the minimum at the equilibrium separation, minimum at the equilibrium separation RE between the atoms, that is R is equal to RE. The energy has its lowest value. Energy has its lowest value means you have to differentiate it. You have to take a differentiation. Du by dr. That's what it is shown in this example. That's what it is done in this example. Hmm? So you have to take force du by dr minus du by dr. Now at equilibrium, you will see R is equal to RE, so force is equal to 0. This force is equal to 0 at equilibrium. So once you differentiate, you will see MA by RE to the power n plus 1 is equal to NB by RE to the power n plus 1. So that implies RE is equal to NB by MA to the power 1 by n minus n. Hmm. So this equation 3 gives the equilibrium separation between the atoms in the molecule. Okay. Or you can express UE or URE is equal to minus A by RE M into 1 minus M by N. So there is a relation between them. All right. This part is clear. Next, we'll move over to something called covalent bond. ପ୍ଲସ୍ ଟୁରେ ବି ପ୍ରାୟ ସମସ୍ତେ ପଢିଥିବ ଟିକେ ଟିକେ ନାଇଁ ଆୟନିକ ବଣ୍ଡ କୋଭାଲେଣ୍ଟ ବଣ୍ଡ ଭେଣ୍ଡରଲ୍ସ ବଣ୍ଡ
Yes, sir.
hydrogen bond. The only difference here is we are dealing with some mathematical equations over here. Certificate mathematical equation पढ़ाए ना थे. Okay. Ionic bond केमती होउची? देखो इलेक्ट्रॉन पॉजिटिव इलेक्ट्रॉन नेगेटिव जनकर गोटे if you take for example NaCl, sodium has 11 outermost electrons and it need to lose one to become stable with 10 outermost electrons. And chlorine, if you take chlorine, chlorine has 17. Chlorine has 17 electrons, outermost electrons. So then chlorine needs one. Chlorine needs one to become stable. And that's how there is transfer of electron from sodium to chlorine. So once sodium loses one electron, it becomes Na plus, and chlorine accepts one electron, it becomes Cl minus. So there are two positive and negative. So there is a pair of ions, I would say, close to each other. So that's why they will get attracted, and that attractive force is nothing but the bonding force. Nothing but the bonding force. Okay. What happens in covalent bonding? Covalent bonding is basically you create orbital electron interact, isn't it? Electron interact. So orbital electrons will interact. For example, if you think of uh, methane, CH4, right? Yeah, if you think of CH4, so then you have C and then the four H atoms, right? The carbon has six electrons and four outermost electrons. And hydrogen has one electron. So what happens? The electron over here and the electron over here, they kind of form a pair which is kind of shared by both hydrogen as well as carbon. So the electron orbitals they interact and form a composite orbital, which kind of counts toward this ability of uh, one atom with and I mean if covalent bond is formed, the electron they form shared electron pairs, and these shared electron pairs they contribute to the stability of both, let's say, carbon and hydrogen, both carbon and hydrogen. So that's your basically covalent bonding. There are various other, depending on, so there you also have studied in chemistry, uh, sp3 hybridization. ସମସ୍ତେ ପଢିଛ ନା ଏଇଟା hybridization?
Yes, sir.
sp3 hybridization, sp2 hybridization. So sp hybridization. So it's like C C C double bond C C triple bond C like that only. Yeah. So these are nothing but covalent bonds. These are nothing but covalent bonds. So pair of electrons are kind of shared by both atoms. Okay. Yeah. ionic bonding, covalent bonding, metallic bonding. Metallic bonding is more like, sea of electrons. In a metal, there is sea of electrons. In a metal, there is sea of electrons, and those electrons interact with each other irrespective of the positive ion core, like in other materials. Okay, so in a metal, electrons in the outermost shell of its constituent atoms can be detached by supplying small amount of energy. According to the theory of metallic bonding, the metal consists of atoms that have given up their outermost electrons to form the electron gas. Okay, so it is treated like an electron gas, which moves throughout the system. The electrical interaction between the positive ions at the lattice sites and the negative electron gas holds the metal together. So what happens? It is not just one electron; it is the collection of electrons which are kind of so. So you can imagine as if ଏଭଳିଆ ଚିନ୍ତା କରିପାରିବ ଯେ ପଜିଟିଭ ଆୟନ କୋର ଗୁଡା ଫିକ୍ସ ହେଇକି ରହିଛନ୍ତି ଆଉ ତା ଚାରିପଟେ ଗୋଟେ ଇଲେକ୍ଟ୍ରନ ର ଫ୍ଲୁଇଡ ମୁଭ୍ କଲା ଭଳିଆ ମୁଭ୍ କରୁଛି. Not one electron, but a bunch of electrons. Uh, so that's how the metallic bonds. Similarly, we have hydrogen bonding and van der Waals bonding. Van der Waals bonding is mainly dipolar interaction, polar non-polar interaction, polar polar interaction, non-polar non-polar interaction. Whether if you go to little bit in deep, like in quantum mechanics, so it is the electron and the nucleus, 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 electron, electron, nucleus, electron. These kind of all kind of sets of interactions occur, and whichever is dominant, that will decide what kind of bonding we will have. I think this is very simple. If all of you slightly go through the text, you should be able to understand. That should not be a problem. Yeah, I'll take a couple of minutes break and then start with something called lattice dynamics. What happens till now? Whatever we discussed is basically static picture, still picture of the system. Now we'll see how exactly what happens when electrons or the atoms vibrate, oscillate. What happens to the crystal structure? Okay, that is done. ଏପର୍ଯ୍ୟନ୍ତ ଯାହା କହିଲି ବୁଝିହଉଛି ନା ବୁଝିହଉନି?
ବୁଝିହଉଛି ସାର୍।
ହଁ, ଟିକେ ପଢିଲେ ଥାର୍ଡ ୟୁନିଟ ଟିକେ ପଢିଲେ ହେଇଯିବ ସେଥିରେ ବିଶେଷ କିଛି କଷ୍ଟ ଜିନିଷ ନାହିଁ. ଲାଟିସ୍ ଡାଇନାମିକ୍ସ ନା ଟିକେ ମ୍ୟାଥମେଟିକ୍ସ କରିବା and then how to do that. Many times questions actually come from this monoatomic chain and diatomic chain that I have discussed. Okay, we'll start with the lattice dynamics. Let us try to understand a little bit from the introduction. In the study of crystal structure and crystal bonding, the previous units, we have assumed, we have assumed, we have assumed that the atoms remain rest at the lattice site. However, the fact is that the atoms in the crystalline crystal oscillate around their equilibrium position. So they are not static; they oscillate around their equilibrium position. Further, for simplicity, we assume that the crystals can be regarded as continuous medium. Crystals are not continuous; they are discrete. But for better understanding, we assume them to be continuous medium. That is, we ignore the fact that is, we ignore the fact that crystalline solid is composed of discrete atoms. Crystallized solid is made up of discrete atoms. We are not telling them, but it is kind of a continuous. Waves generated, waves generated by oscillating atoms such as a continuous medium are referred to as elastic waves or lattice waves. Elastic waves or lattice waves. What are elastic waves or lattice waves? It is they are rising because of the oscillations of the atoms in a system. Okay. The assumption that the solid is homogeneous and behaves as a continuous medium is a valid assumption as long as the wavelength. So when exactly this is valid? As long as the wavelength of the elastic wave is much greater than the interatomic separation. The wavelength of the elastic wave is much larger than the interatomic separation. It is valid. So you can imagine, yes, this solid is kind of continuous only when the wavelength is much larger as compared to interatomic distances. So then the wave does not see discreteness; it kind of sees a continuous medium. A more general analysis of the generation and propagation of elastic waves in a solid must consider a collection of discrete atoms arranged along the periodic lattice. Okay. Now, what happens here? So, while discussing the dynamics of a chain of identical atoms, dynamics of we'll consider only one-dimensional case now. We consider only one-dimensional case now. Later, it can be converted into three-dimensional one. And the dynamics of the chain of identical atoms is into the best lattice. So, what do we do here? Here, it is called concept. We are treating each atom like a harmonic oscillator, or it is kind of oscillating. It is kind of oscillating around its mean position. It is oscillating around its mean position. But this is not one. This is not one. This is not just one. There are many. So here is one. Here is one. Here is one. So how exactly this will oscillate in this direction? That will affect the oscillation of this direction. Oscillate affects the oscillation of this one. This one. Huh. And the assumption here we are taking that Let's say our particular concentration is on this atom. So then this oscillation will be affected by either this one or this one. This is not going to affect, or this is not going to affect the oscillation of this particular atom. That is our assumption. In reality, that will affect, but the percentage of affection, how much it will affect, that will be much less. So nearest neighbor will affect more, and next nearest neighbor or next to next nearest neighbor, they will affect very much less. Okay, so that's what is kind of explained in this mathematical equation. So what exactly it is telling? All of us we know. Let me write down the simple form of the equation. F is equal to minus kx, right? That is simple harmonic motion. Now F is what? M d square x by dt square is equal to minus kx, where k is spring constant. Okay, this is what we know. This is also similar. It is telling M is the mass, m d square un by dt square, d square un by dt square. That should be equal to what? Minus kun. That should be equal to minus kun. That is simple. But it is not just one atom. It is not just one atom. There are a bunch of atoms which are kind of interacting with each other. That's why instead of taking just one, we'll take un minus 1 plus un plus 1 minus un. So we are taking the separation between the two nearest neighbors. The separation between two nearest neighbors. So instead of just taking their position, we are taking the relative position of one atom with respect to its nearest neighbor. Okay. And then if we try to simplify, so m d square un by dt square equal to k un plus what minus un minus plus un minus 1. Yeah. And if we assume that un is equal to un is of this form, if we think that un is of this form, what is this form? A e to the power I minus I omega t plus kx and naught. So this is simple plane wave solution. This is simple plane of solution, right? A exponential e to the power minus I omega t is the time dependent part, and a e to the power I k x naught. A e to the power I k x naught. This is that is simple, simple progressive way. If we substitute that, if you substitute, so if we use one equation over here, if we use this equation, yeah, this equation, let's say this is equation 1 and this is equation 2, then what we will do? You instead of un, we will try to determine what is the value of d square un by dt square, d square un by dt square. That should be equal to instead of k un plus 1 minus 2 un plus un minus 1. So if we use that, we will somewhat get this equation. This somewhat get this equation. And if we simplify this way, we will get equation like this, or W is equal to this. So, this what exactly is giving? It is a relation between W and K. Relation between W and K, or H cross omega and H cross K, or energy and moment. Energy and right? Yeah. So this is one way. So this is called dispersion relation for monoatomic lattice. This is also called dispersion relation. Dispersion relation So, mm, mm, what happens in a diatomic? So in case of a diatomic, instead of having here monatomic is all are M. This is also M. This is also M. This is also M. But in diatomic, this will be M1. This will be M2. This will be M1. This will be M2. Like that. So the mass will change. All right. Do you understand up to this point?
Yes, sir.
Yeah. So this monatomic and diatomic are many times asked as questions. So I think all of you should practice monatomic dispersion relation diatomic. I know these 4 to 8 classes are not sufficient to explain everything, but I should be able to give you a foundation where you know what is crystal structure, how crystal structure is determined, how exactly the lattice points interact, so that they give us to different dynamics. Any questions? If you have any questions, you can ask. Later on, also, depending on the forum, you can post your questions. Wherever is available, you can answer that. As you can see over here, it has taken, instead of M1, M2, it has taken capital M, smaller. Capital M, small. Interesting. ସେ ଟିକେ ପଢିଲେ ହେଇଯିବ ଏଗୁଡା ବିଶେଷ କିଛି ନାହିଁ only just you to follow this simple mathematics of solving differential equations. You are free to ask questions. No. Any question is good. No questions? ପଢ ଟିକେ ପଢିଲେ ଯାଇ question ବାହାରିବ ଟିକେ ଭିତରୁ ପଶିଲେ ପ୍ରାକ୍ଟିସ କଲେ ସେଟା ବୁଝିଥିବ ନ ବୁଝିଥିବ ବାହାରିବ। Okay, if no more questions, then I will possibly stop it here. So at least I have given a basic understanding of the basics, of the starting points of crystal structure, reciprocal lattice, crystal structure determination, and all. So based on that, you can possibly proceed in other parts of
Sir,
the.
give a brief idea about the other two means blocks of this paper.
Yeah,
Means
yeah,
what would
yeah. I mean, that will be more into. So whatever we've discussed now, that is
okay.
more statics. That is more statics. Okay. So that is like a static picture. You're taking a picture or a video. If I try to explain, your uh, how to say, if you take one picture, it does not tell many stories. But if you take a video, it kind of tells you a story. Similarly, if you just take one static understanding of the crystal structure, that is very limited. But what happens to the electron, what happens to the lattice when they vibrate, how they interact, so that gives the whole picture, and that gives rise to the concept of band gap. Yeah. Later on, so in the subsequent chapters, you will be able to understand band gap. But for that, I suggest you go through little bit of electrodynamics and uh, your, of course, mathematical is required, but mostly quantum mechanics and electrodynamics are kind of required to understand these mathematical concepts, which are kind of discussed in block 2 and block 3. Yeah. You have all of your material, right? The study material you have, right?
Yes, sir. Only soft
Yeah.
copy.
Okay. Yeah. So if you look at here lattice dynamics, then thermal properties. Thermal properties again, those are related to lattice vibrations. What we discussed now, monatomic, diatomic, those are lattice vibrations and lattice dynamics. Based on that, thermal properties will evolve. So from there you will get Einstein model, Debye model of heat capacity. Uh, okay, so that part is there. If I come to, let me see what else is there. Mm, Block 3. In block 3, you have dielectric properties, paramagnetism, diamagnetism, and simultaneous magnetic order. Uh, so these are again based on not static picture. It's partly static and partly dynamic. How exactly the electron interact, how exactly the fields interact. Those are coming under dielectric and magnetic properties. But my point is, you should be, once you start reading, you should be able to understand. It is not completely kind of new. Based on your understanding on crystal structure and lattice dynamics, you should be able to understand. Okay. Any more question? All right. If no more question, then I'll proceed this topic here. Good luck.